Imagine a material, right? Lighter than aluminum, but actually stronger than steel. You see it everywhere. Aerospace, sports gear, you name it.
Uh,
Now, what if that same material could, well, actually help us fight climate change?
that's a pretty compelling idea.
Exactly. And it's right at the heart of our deep dive today. We're digging into a study called Techno-Economic Assessment of Atmospheric CO2-based carbon fiber production enabling negative emissions.
Quite a title.
It is, but it gets right to the point.
Mhm.
This research looks at a really novel way to make carbon fiber CF, people often call it, using CO2 captured straight from the atmosphere.
And we desperately need these kinds of innovative ideas, don't we? I mean, the Paris Agreement, the IPCC reports, they all make it clear we need massive negative emissions.
Huge amounts. We have to literally pull CO2 back out of the air.
Yeah, and a big challenge is, how do you do that? How do you store it securely long term? We have things like BECCS and DCCS capturing and storing CO2 underground or through mineralization.
Sure, those are important.
But this study explores something different, turning that captured CO2 into a valuable, durable product.
That's the twist. Carbon fiber itself, it's already a big deal. The market's growing fast, and it's almost pure carbon, like up to 98% by weight.
Incredible stuff. Lightweight, super strong, resistant to heat, chemicals.
All those properties mean it has massive potential in loads of industries. So the core question this study asks is, well, could we link that growing demand for CF with the urgent need to remove CO2? Could making it actually be a way to get negative emissions?
That's the whole idea behind techno-economic assessment of atmospheric CO2-based carbon fiber production, enabling negative emissions. And our focus today is really on what this study found about whether this is, feasible. What's the potential?
Right. It looks at different ways to make it using two main starting materials or precursors, polyacrylonitrile, PAN for short, and pitch.
And importantly, the study digs into the economics, especially for that PAN route using atmospheric CO2.
And the potential scale. It's pretty staggering, actually. Based on their market projections for carbon fiber, this study suggests that by 2050, making CF this way could remove at least 0.7 gigatons of CO2 from the air every year.
0.7 gigatons, just to put that in perspective, that's a really significant chunk of the negative emissions people think we'll need.
Definitely a number that makes you sit up and take notice.
So, okay, to really get how this new idea works, it probably helps to quickly understand how carbon fiber is normally made, right? The conventional ways.
Good point. This study outlines the two main paths. The most common one uses that PAN precursor, which usually comes from petrochemicals like propene or propane.
And the other route uses pitch, which you can get from ethene, another petrochemical. Figure 1 in the paper gives a nice simple overview if you imagine the value chains.
Let's start that conventional PAN route then. The first big step is something called amoxidation.
Sounds technical.
It is a bit. You take propene, or maybe propane, react it with ammonia and oxygen using a catalyst, and it gets pretty hot, like 400 to 510 degrees Celsius.
Okay, and that makes...
acrylonitrile, AN. That's the key building block molecule for the PAN.
Got it. So you've made the building blocks, then you link them together.
Exactly. That's polymerization. You link those AN molecules into long chains. They usually add a little bit of something else, methyl acrylate, just to tweak the final fiber properties.
And that happens at lower temperatures.
Much lower, yeah. Maybe 25 to 65 degrees C. Then they dry the resulting PAN material.
Okay, so AN to PAN. What's next?
The final, really critical step, carbonization. First, they heat the PAN fibers in air, maybe 200 to 300 degrees C, just to stabilize them.
Right, kind of preps them.
Then comes the intense part. They heat them way, way up, usually somewhere between 1,000 and 1,400 degrees C without oxygen.
Wow, okay.
And that extreme heat basically drives off almost everything except the carbon. What's left is that strong, lightweight carbon fiber structure. It's almost like baking off all the impurities.
A very, very hot baking process.
Okay.
So that's the PAN route. What about the pitch route? The study mentions that too.
Right, the pitch route. According to the study, it typically starts with ethene. That gets chlorinated to make vinyl chloride monomer, VCM.
VCM, okay.
Then, similar to the PAN route, that VCM gets polymerized, linked into chains, to make PVC, polyvinyl chloride, usually in water around 50 to 70 degrees C.
PVC.
Oh.
Yeah, no PVC. But how do you get from PVC to carbon fiber pitch?
This is where it gets different. The PVC goes through pyrolysis. That means heating it really hot, but without oxygen to break it down. Then further heat treatment up to about 430 C creates something called mesophase pitch.
Mesophase pitch.
And that pitch material is then spun into fibers, fine little threads.
Okay, so now we have pitch fibers. still need to carbonize them.
Yep. Just like the pan fibers, they need stabilizing first, heated in air, maybe up to 320 C this time. Then a carbonization, which can hit around 900 C. And often they do a surface treatment with steam too, around the same temperature.
So similar final steps, but a different path to get the initial fiber.
Exactly. And one thing the study really flags is that both these conventional ways use a lot of energy.
Yeah, I saw that. The numbers quoted in the literature are all over the place, aren't they? From just over 2 kilowatt hours per kilo of CF up to nearly 320.
That's a massive range. It suggests efficiencies vary hugely.
And all that energy use means a hefty carbon footprint, right? Especially with natural gas.
Definitely. A lot of natural gas gets burned, particularly for cleaning up the exhaust gases. They use something called a regenerative thermal oxidizer, an RTO unit. It's needed because the process makes some nasty stuff.
Right. So the footprint ends up being somewhere in the range of, what, 24 to 31 kilos of CO2 for every kilo of carbon fiber produced.
That's what the study reports from the literature, yeah. Pretty significant.
And you mentioned nasty stuff, toxic byproducts.
Yeah, the study points that out too. The pan route can release hydrogen cyanide, which is highly toxic. And the pitch route, during that pyrolysis step, can generate things like hydrochloric acid and sulfur dioxide. Pollutants.
Okay, so conventional CF,
Yeah.
energy intensive, significant carbon footprint, and some potentially harmful emissions. That sets the stage nicely for the alternative.
Exactly. Which brings us back to the core idea in techno-economic assessment of atmospheric CO2-based carbon fiber production, enabling negative emissions. What if we could ditch the fossil fuel feedstocks entirely?
And use CO2 from the air instead.
Right. Use CO2 captured directly from the atmosphere as the carbon source. The study calls this electricity-based CF production, or ECF, sometimes power to carbon fiber, PTCF.
It's a power to X concept, essentially.
Yeah.
Using renewable power to make something valuable.
So how does it actually work? Let's stick with the pan route first because the study goes into more detail there. They call it MERI-OH to CF pan.
MEOH for methanol, I assume.
Exactly. The very first step is capturing the CO2. The study assumes using direct air capture, DAC. You can think of DCF units as big machines that filter CO2 out of the ambient air.
Okay, so you got your CO2. How do you turn that into the precursor for PAN?
Right, so the CO2 needs to be converted. The next step is making methanol, MEOH, from that captured CO2. This needs hydrogen.
And the hydrogen comes...
Electrolysis. Using electricity to split water into hydrogen and oxygen. And crucially, as the study emphasizes, that electricity has to be renewable solar, wind, whatever, otherwise the whole low-carbon point is lost.
Makes sense. Clean electricity for clean hydrogen.
And actually, hydrogen isn't the only thing made with renewables here. Remember, the conventional pan route needs ammonia for that oxidation step.
Ah, right.
This ECF process proposes making that ammonia too, using renewable electricity in a Haber-Bosch unit. It also needs nitrogen, which you can get from the air using an air separation unit, an ASU. So more clean electricity inputs.
Okay, so renewable power makes the hydrogen and the ammonia. We've got methanol now from CO2 and hydrogen. How do we get to propene, which we need for the acrylonitrile?
Good question. There are processes to convert methanol into olefins like propene and ethene. The study focuses on the methanol to propylene, or MTP, route specifically for this PAN pathway.
MTP.
These are catalytic processes, again, running quite hot, maybe 400 to 500 degrees C.
Right, and is there anything clever about the energy use here?
Potentially, yes. This is quite neat. The study points out that the oxidation step itself, making the acrylonitrile, actually releases heat around 450 C.
Oh, interesting. That's in the same ballpark as the MTP process needs.
Exactly. So there's potential for heat integration. You could maybe use the waste heat from oxidation to help power the MTP step, which would reduce the overall energy needed. Nice synergy.
That makes a lot of sense for efficiency. Okay, so MTP gives us propene. Then what?
Then, essentially, we follow the steps we already discussed for the PAN route. Oxidation using the propene and the renewably made ammonia, polymerization to make PAN, and then the final carbonization.
But how is the energy supplied for those steps in this ECF version?
Yeah.
Especially that super hot carbonization.
Right. The key difference here is the energy source. The study assumes the high-temperature heat for carbonization, that 1200 to 1400 C range, comes from electric heaters.
Powered by the same renewable electricity.
Precisely. And any lower temperature heat needed, like for polymerization, could come from efficient heat pumps, also running on clean electricity. Figure 2 in the paper lays out this whole ECF via PAN pathway quite clearly.
Okay, so it sounds plausible chemically. What about the numbers? Does it actually work out in terms of carbon removal and energy use?
Yeah, the study provides a mass and energy balance. They looked at a scenario for 2030, and for every ton of CO2 you successfully remove from the atmosphere using this process,
Yes.
you produce about 0.287 tons of carbon fiber.
Okay. And the energy cost?
It takes about 56.9 megawatt hours of electricity per ton of CO2 removed.
56.9 megawatt hours. That sounds like quite a bit of electricity.
It is a significant amount. But look at the flip side, the carbon storage.
Right. How much CO2 gets locked up per ton of fiber?
About 3.5 tons of CO2 removed from the atmosphere for every ton of ECF produced. That's very efficient storage, close to the theoretical maximum you could get based on the carbon content of the fiber itself.
That is a high ratio. So you're effectively concentrating and storing atmospheric carbon in a very dense, stable form.
Exactly. And interestingly, the study projects that the electricity needed will actually go down over time.
Oh, why is that?
They expect efficiency improvements in those supporting processes like DA and electrolysis. So by 2050, they estimate it might only take 53.7 megawatt hours per ton of CO2 removed. Still a lot, but better.
Which part uses the most electricity? Is it the DAC?
Actually, no. According to this study, it's the electrolysis making the hydrogen. That's the biggest energy hog in the whole chain.
Why so much hydrogen? Just for the methanol?
Mainly, but also for making the ammonia and even for making some e-methane, which gets used in that exhaust gas treatment step, the RTO.
Ah, right, the RTO. Does using e-methane there affect the carbon balance?
It's an important point they make. To get a net removal of 1 ton of CO2, you actually have to capture more upfront, about 4.135 tons.
Okay, why the extra?
Because some of that captured CO2 is used to make that e-methane for the RTO. But they assume that cycle is carbon neutral. The CO2 used to make the methane is released again when it's burned in the RTO, so it doesn't count against the net removal achieved by locking carbon in the fiber.
Got it. So 4.1 tons captured to achieve 1 ton stored in the final product. Still a net removal.
Definitely. Now, the study also touches on using the pitch precursor route for ECF, though maybe in a bit less detail.
Okay. How would that work? Still starting with methanol.
One pathway they mention is MEOH to CF pitch. So similar start, captured CO2 to methanol, but then instead of MTP for propene, you'd use methanol to olefins, MTO, to make ethene.
And ethene is the precursor for the pitch route.
Right. Then you'd presumably follow the steps for pitch production, polymerization, pyrolysis, spinning, carbonization using renewable energy.
Is there another pitch pathway mentioned?
Yes, briefly. They call it CH4 to CF pitch. It involves an extra step, taking methane, CH4, and converting it to ethene through something called oxidative coupling. Then you proceed from ethane as before. Figure 3 in the paper shows these.
Oxidative coupling of methane. I seem to recall that being tricky.
It is. The study acknowledges it currently has low conversion yields, maybe 25 to 50%, and can produce unwanted CO2 and carbon monoxide. So technologically less mature, perhaps.
And you said the pitch routes were covered in less detail overall.
Yeah, the authors note there's just less detailed information out there, especially on things like how to handle the waste or residues from the pitch stabilization and carbonization steps compared to the pan route.
So maybe more uncertainties there.
Seems that way. Which is likely why the economic assessment really drills down on the pan route.
Right, the economics. Let's get into that. How does this ECF stack up cost-wise?
Okay, so techno-economic assessment of atmospheric CO2-based carbon fiber production enabling negative emissions calculates 2 main things. The levelized cost of carbon dioxide removal, LCOCDR.
Basically, the cost per ton of CO2 you remove over the plant's life.
Exactly. And the levelized cost of carbon fiber, LCOCF, the cost per kilogram of the actual product. They use standard financial modeling, assuming a 7% cost of capital, and the plant running 95% of the time, so high availability.
Okay. What are the main cost drivers, just looking at the process itself, leaving energy aside for a moment?
Figure 5 in the study breaks that down. Among the auxiliary processes, the support systems electrolysis for hydrogen and the direct air capture units are the big ones.
Makes sense. Those are complex technologies.
And the core chemical conversion part, the MEOH to CF pan cluster, also makes up a decent chunk of the process cost. But they do project costs coming down slightly, maybe 7.6% total process cost reduction between 2030 and 2050.
Driven by improvements in DAC and electrolysis, you mentioned.
Mostly, yeah.
Yeah.
Learning curves and scaling for those technologies.
Okay, but that's without the energy cost. What happens when you add that in?
Yeah.
Because we said it uses a lot of electricity.
Right. And that's where figure 6 comes in, and it changes the picture quite a bit. If you look at it only as a way to remove CO2, it looks pretty expensive, especially at first.
How expensive?
The study estimates the cost per ton of CO2 removed the LCOCDR at around 767 euros in 2030.
Wow. Okay, that's high compared to some other potential carbon removal methods.
It is. It does come down in their projections to about 2,949 euros by 2050, but still, just for the removal aspect, it's costly.
And this is the crucial but, isn't it? You're not just removing CO2.
Precisely. You are making a valuable product. Carbon fiber. High demand, high performance.
So if you factor in the money you could make selling that carbon fiber.
Then the whole picture changes. The study suggests that when you account for selling the ECF at an assumed market price, the whole thing could actually be economically attractive, maybe even profitable, as early as 2030.
So the product pays for the removal, essentially, or at least a large part of it.
That seems to be the key finding. The value of the CF itself could make the business case work.
And what if there's also a price on carbon? Like payments for negative emissions?
That makes it even better, obviously. The study includes that possibility. With carbon compensation factored in, they estimate a net benefit profit of maybe 557 euros per ton of CO2 removed in 2030, rising to over 1,400 euros by 2050.
Okay, so carbon pricing could really accelerate this kind of technology.
Absolutely. It turns the climate benefit into a direct financial one, too.
What about the cost of the carbon fiber itself, the LCOCF? How does that compare to conventional CF?
Good question. The study estimates the cost of ECF at about 13.1 euros per kilogram in 2030.
Okay, and conventional CF is typically what?
Prices vary, but maybe in the 15 to 25 euro per kilo range.
Yes,
depending on
something
material.
like that, yeah. So 13.1 is already potentially competitive, and they project that cost dropping further to 11.5 euros in 2040 and down to 10.3 euros per kilo by 2050.
10.3 euros per kilo by 2050. That sounds very competitive, potentially cheaper than conventional methods might be by then, especially if fossil fuel prices rise or carbon taxes increase. Exactly. They also broke out the cost just for the pan precursor made this way, estimating that at 12.9 euros per kilo in 2050.
Interesting. So the economics look potentially promising, but these are projections. They must depend on assumptions. Did they do a sensitivity analysis?
They did, yes.
Yeah.
To see how things change if key factors are different, Figure 7 looks at this. They tested sensitivity to electricity costs, the capital cost of the main chemical plant, the plant's lifetime, and its availability factor.
And what's most sensitive? Electricity cost, I bet.
You guessed it. Especially in the new term, like 2030, when electricity prices are assumed higher and the tech is less mature, costs go up pretty much linearly if electricity gets more expensive.
Makes sense, given how much it uses. What about the capital costs, the initial investment?
That sensitivity shows a slightly different pattern. Changes in the capital cost of that main MEOH to CF pan cluster actually have a bigger impact on the projected 2050 costs than the 2030 costs.
Suggesting that achieving those long-term low costs really depends on getting cheaper plants built.
That seems to be the implication, yeah. Reducing the upfront investment becomes more critical further out.
Okay. What about lifetime and availability? How much the plant runs?
Lifetime has a big impact, almost an exponential relationship. If the plant doesn't last as long as assumed, costs shoot up much faster than they decrease if it lasts longer. Durability is key.
Right. Need reliable, long-lasting equipment. And availability.
Also crucial, costs are highly vulnerable to the availability factor. Even small drops in uptime, the plant not running consistently, lead to significant cost increases.
So these things need to run reliably, pretty much constantly, like baseload power plants.
That's the idea. High utilization is essential for the economics to work.
Okay. And did they look at sensitivity to the selling price of the carbon fiber, since that seems key to profitability?
Yes, Figure 8 covers that. It shows how the net profit changes depending on the market price for CF, both with and without that carbon compensation payment factored in.
And is it very sensitive?
It seems most sensitive earlier on, in 2030. The analysis suggests that without any carbon payments, even just a 10% drop in the assumed CF selling price could make the whole thing unprofitable in that year.
Ouch. So market price risk is significant, especially early on.
It is, but having that carbon compensation provides a much bigger cushion against those price swings, makes the business case more robust.
Okay, that all makes sense. So stepping back, What are the main discussion points or challenges the authors raise?
Well, they definitely acknowledge the lack of really detailed, up-to-date process data, particularly for those pitch-based routes. That makes precise modeling tricky right now. More open data would help future studies.
A common challenge in techno-economic assessments of emerging tech.
True, but they are optimistic about the potential competitiveness of ECF down the line. They argue that as fossil fuels get more expensive and carbon emissions carry higher costs, this electricity-based route could genuinely compete with or even beat conventional CF production. They cite some other cost estimates that support this view.
And beyond just replacing conventional CF, what about new markets?
That's a really exciting aspect. They talk about the potential for ECF to substitute materials like steel and aluminum, especially in cars for lightweighting, which saves fuel or extends battery range.
Huge potential market there.
And also in construction, using carbon fiber in textile reinforced concrete. This could mean thinner, lighter concrete structures, and importantly, it could reduce the amount of cement needed.
And cement production has a massive carbon footprint itself.
Exactly, so you get a double win. Storing carbon in the fibers used in the concrete and avoiding emissions by using less cement.
That's a powerful combination.
So the study really frames ECF as a potentially valuable addition to our toolkit of negative emission technologies.
And distinct from something like BECCS because it's less reliant on land area, right? It mainly needs air, water, and clean electricity.
Right. DCS is the key enabler there, and it's important to see it, as the study points out, as both CCS carbon capture and storage in the durable fiber and CCU carbon capture and utilization, using the CO2 as a feedstock.
It's doing both, storing and utilizing.
How does the potential scale that zero point 0.7 gigatons per year by 2050 number compare to other negative emission options?
Well, estimates for other nets like BECCS, afforestation, enhanced weathering, they often fall in the range of maybe 0.5 to 5 gigatons per year each. So zero point 0.7 is definitely in the same league, a potentially significant contribution.
So it could be a major player.
Could be. And the study briefly mentions a similar concept for making silicon carbide using electricity and capture CO2, another potential pathway.
Interesting. And a key advantage they highlight for ECF is lower economic risk compared to just storing CO2.
Because you have a product to sell.
Exactly. The carbon fiber has inherent market value, which helps drive the economics even without relying solely on carbon removal payments.
Makes the investment potentially less risky.
Yeah.
What about future research needs? Where should efforts focus now?
The study flags several areas. Getting more current, detailed cost data for all the chemical steps involved is crucial.
Right. Better inputs for the models.
Also, scaling up these models to reflect future industrial-sized plants. Looking hard at energy efficiency gains, they reference some U.S. Department of Energy work there.
Squeezing more efficiency out of the process.
And doing deeper analysis of the water and nitrogen requirements for the whole system, which could be substantial, plus more detailed sensitivity and maybe dynamic modeling over time.
One last point you mentioned earlier was about the fiber quality.
Yes, a potential limitation, they note. The exact temperature used during carbonization affects the final properties of the fiber, like its tensile strength. So the ECF produced might not automatically suit all existing carbon fiber markets, especially the very highest performance ones.
So process optimization might be needed depending on the target application.
Exactly. Tailoring the ECF production for specific market needs might require more research.
Okay, so wrapping things up then. This deep dive into techno-economic assessment of atmospheric CO2-based carbon fiber production enabling negative emissions has really uncovered a fascinating approach.
It really has. It's this idea of using CO2 from the air to make a high-value product, carbon fiber, and in doing so, potentially decarbonizing CF production and achieving significant negative emissions. A double whammy.
And the numbers are compelling. Potentially 0.7 gigatons of CO2 removal per year by 2050, based on their market growth assumptions.
And the cost projections suggest this ECF could become cost competitive with conventional CF, maybe reaching around 10.3 euros per kilo by 2050, according to this study's analysis.
And while maybe it's not cost-effective just for the carbon removal aspect right now,
the fact that you're making a valuable product creates a potentially strong business case on its own, with that huge co-benefit of atmospheric carbon removal.
it really represents an interesting convergence, doesn't it? Industrial manufacturing, cutting-edge carbon capture, and sustainable materials all coming together.
It certainly makes you think about the kinds of innovative solutions we might see more of as we tackle climate change, combining problems to create solutions.
Indeed. And that brings us to the end of our exploration of the study. Techno-Economic Assessment of Atmospheric CO2-Based Carbon Fiber Production Enabling Negative Emissions.